Perfect. So we're going to open the discussion section of this session. So yeah, if you have a question, I see Andy Rifkin raising his hand over there.
Yeah.
And maybe we could have all the speakers from our session maybe gather around here to answer a question. That would be probably easier.
Oh, let me go get the thing. Have a cue. Thank you. This is for Dan and William Frederick. So I'll point out that when you're looking at the thermal fracturing question, and I'll point out that there have been a number of recent papers done by some early career folks that you should definitely look at. Jamie Malaro at JPL has been looking at it and looking at it on the moon. Charles Elmire is a grad student at Hopkins who's also been looking at it and found that there is an optimal size at which this effect is strongest. And as you might imagine, that size is about the skin depth, the thermal skin depth, which is a few centimeters. So I guess the question then would be, for smaller objects, for meter to few meter size objects in space, they're mostly going to be isothermal because either they're spinning fast enough or they're small enough that you're not necessarily going to be able to support large temperature extremes across them. So you might expect thermal fracturing to shut off. Is that consistent with, with what you're seeing, and how well do you think your thermal cycling experiments are matching what you might expect on the kinds of size objects that you're trying to compare them to?
Well, what I was envisioning was meter scale, multiple meter scale bodies on a larger body. So it would be rotating slow enough that you would actually have a thermal pulse varying a couple hundred degrees C. My thought here is that most of these boulders did reside on a larger object at one time before being separated in some fashion, and what you see in the bolide data makes me think that you have a surface around these things that's covered by a relatively weak dusty layer.
That would have been maintained after separation from the parent body.
That would have been maintained after separation from the parent body. And I would interpret that as maybe your thermal skin depth. Yeah, I'm aware of at least some of these papers that you're talking about, and I think it's very interesting in trying to hone in on how the surface of this material evolves over time. And I think that's a very interesting subject. And it has stuff to do with applications to the moon, to asteroids, and to potentially using this stuff for resource potential.
And I'll just make two quick comments on that. First of all, Jamie's work is really cool. And I mean, it's your talk, right? But her stuff is cool. So
her stuff is cool.
Her stuff is cool. So the second thing is that breakdown rates can't be too fast because we have cosmic ray exposure ranges for meteorites. Many people argue they come from meter-size objects or so. And those timescales are often on the order of many millions of years to tens of millions of years. And if the breakdown rates were super fast, then everything would ultimately have to have a really short cosmic ray exposure age, and we just don't see that. So if we're interpreting that correctly, then that means there has to be a limit to what happens.
Yeah, and I think what we find is that from a mineralogical point of view, you can drop the surface strength some amount. We were getting about 50%. But then you hit a steady state, because essentially what's happening is that the different coefficients of thermal expansion have essentially done their damage. And once you essentially elbow your way into more space, then you stop doing work. Yeah. And so you have a relatively weak layer that's a few centimeters. And further breakdown probably has to await other things like micrometeorites, which take longer.
We'll try this elbowing principle tonight when we go for the beer, you and I.
That's right.
So other questions or comments or topics, or what do you have? So
I'm a spectroscopist, and my question is for Amanda. Can you describe why the presence of organics would shift the absorption edge to the blue? I just didn't. I wondered about the electronic bands, or you were mentioning maybe nanophase iron or organic. So it wasn't or carbon.
I said iron or carbon.
Okay, so is that a
so I think that it would be like amorphous carbon or graphitized carbon that would be very spectrally flat in that range. And so, like I said, I still need to do some modeling of it, but I think it ought to depress the albedo, flatten it out, but then maybe a phyllosilicate signature could be strong enough at the shortest wavelengths that that's where it kicks in.
Okay, so linear combination of absorption properties. You're thinking of a linear combination of absorption properties, but not necessarily like a nano size of something. It's really the combination of absorber and.
Yeah, I mean, it could be. I do still think it could be nanophase iron. Some of those, some of the maybe chondrules may have enough olivine in them that they could be present on the surfaces of the asteroids, or at least was present, that it got weathered and became nanophase iron. That would also have a similar effect. But I think in our spectral models we can distinguish between the two.
Because my impression was that if comparing the meteorite data, there are a lot greater differences between samples, whereas most of the asteroids seem to have a similar turn on in wavelengths to the absorption band at shortest wavelengths. Is that right? Like there was more uniformity amongst the bodies than there was amongst the meteorite samples?
I only showed 2 meteorites. There's more to look at, so I'm not sure if I'm ready to commit to that statement.
Thank you.
Okay. Other comments, questions? Well, all the way back here. You're going to save me a walk. Oh, see, there we go. Okay. I knew I'd guilt you guys into saying something here. So,
Dave Morrison again. I'm partly repeating what I already said to Dan, but maybe the rest of you have some insights. I'm truly concerned about taking meteorites, a few percent of the original asteroid, and using them to determine the properties of the asteroid. I would think at the very least you'd want to somehow analyze light curves, for instance, see how the asteroid comes apart, try to see if that's consistent with the meteorites that you find later. But just asserting that meteorites and asteroids are similar bothers me.
Well, that's why I looked at bolide light curves and shapes of boulders on asteroids and did some experiments. The problem is that we have an imperfect data set, but it is the data, that is our data set. And so I'm not asserting that what is lying on the ground here is a perfect example, but it is something that you can learn from. It is reality, and reality is telling us something. And when I started this, I blithely assumed that that showers were far more prevalent than boulders in the fall collection. And I found out that reality told me I was dead wrong. And so that's why I am sharing this with you, is it's a data point, and a data point that is not generally known. So I'm not sure I know what it means, but it's a piece of data. When I was an undergraduate, I had a job doing ice core oxygen 18, and we did this equatorial ice sheet in the Andes, Calcaya. And we got this data that we just didn't understand. It had lots of high frequency noise. And it was 10 years later that somebody pointed out that, but that was reality. We repeated it 4 times, and that's what it was. So we thought it was wrong, but we published it anyway. And it turns out that that was a record back 700 years of El Niños. The fact that we didn't understand it didn't change reality. Reality was telling us something, we just don't understand it. So this is a piece of reality. I throw that out. Maybe it doesn't make any difference, but reality is telling us something.
Dan, I have a question related to
Oh, okay.
this question. And it's, in the case of Omahatusita, the estimate is that 99.9% of the meteoroid was, I know you don't like the word meteoroid, but the asteroid was lost in the atmospheric entry.
Yeah.
And it seems like there's a similar estimate for Chelyabinsk.
Yeah, I don't know what the number is for Chelyabinsk.
Right.
I think it's in that order.
It's, yeah. And so, but you were saying 80 to 90%. The two cases that have been measured seem to be more like 99.9%. So it could be that there's, so Dave, it could be that there's a lot more that we don't know. And about what these guys lose in the atmospheric entry and how it's lost.
Well, I'm quoting the bolide people on the 80 to 95%. So I don't, that's something that I don't feel qualified to.
And it could be that it varies from 80 to 99%.
Oh, well, I think the whole point is that it varies quite a bit depending upon the conditions of entry.
Oh,
Okay. Catherine has this really neat pebble accretion model of dumping carbonaceous materials into the asteroid belt. And so this is a question now for the spectroscopist. Is there something smart that you can do with your data to test her idea?
That's the motivation. That's one of them. We want to put constraints on their models. Yes. For
But I think also that's what she's starting with, right?
Yeah. I
You
mean,
showed
yeah.
at the beginning, it's all mixed up. How'd that happen?
Yeah. Are there any more constraints I should be using to
Right.
constrain these models?
or related to this, actually, I was going to ask Amanda this question, but I'll maybe just ask it more broadly, is that there seems to be, I think there's spectral differences between what we used to call P's and D's, and what do we call them in the new DeMayo alphabet? Are they still P's and D's?
I think they're still pieces.
Okay, so P's and D, for those in the audience that don't follow the alphabet soup of spectra, it's basically these are objects which are pretty pronounced in a red slope under a spectra. Is that fair to say? Okay, compared to C-types, which are more flat. And you could make an argument that in the Trojan asteroids and as you go out in the solar system, we see a lot of P and D types. And then a lot of the C types we have are mostly in the asteroid belt. And so there would seem like there's a difference. And I suspect it's related to Catherine's work, if it's right, of certain P's and D's come from a certain zone and C's come from a different zone. And so it seemed like that's something you could test. And I wanted to know from Amanda's data, do you have any P and D data in your data set?
No, the closest thing we have.
Can you please use the microphone?
The closest thing we have is data of, it's probably not that close anymore, Phobos and Deimos. But, because they are P and D like, but probably not P and D anymore.
Well,
Or maybe they are.
Maybe they are.
yeah, go to Robin's talk, or tomorrow Robin's going to talk about the origin of Phobos and Deimos, and she'll make some predictions about how hot Phobos and Deimos got. And so then the question is, can you have really hot objects still maintain the same spectra as primitive? Are they primitive guys or not? That's a good question. So,
Sample return.
yeah. Anyway, it's a really interesting question, and it's something I'm working on now, and we'll see where it goes. But yeah, we should have an offline conversation on that.
But to address that comment, the Trojan asteroids look a lot like the nuclei of comets. And so that is one of the observational constraints that supports some of the dynamical arguments. And so we're trying to continue to provide observational constraints. Some of them may not make sense right now, but I'm sure the dynamicists will come up with a model that will use them as a boundary condition.
I think we're almost reaching the point where we can start to ask like useful questions, I think, which is, yeah, rather than dumb things. Whether we'll have answers, I don't know, but asking questions is good. Any other comments? I just think we should break. What do you guys think? Oh, no, Paul's going to stop us from, sorry, Paul.
So Paul Abel, NASA Johnson Space Center. So Umberto, you and I were talking in the car on Monday, and we had a great conversation about 2008 TC3 and Omahatusita. And maybe you can go into it a little bit more detail for the rest of the audience, because I think it's interesting. So the spectroscopic observations of 2008 TC3 were F-type.
Yeah.
So I think it'd be interesting to go into a little bit more detail on why you think there's a possibility that Ryugu and Bennu, which are C and B respectively could have some Omahatusita type materials on them, seeing as that they're slightly different spectral class than would have been identified for 2008 TC3.
That's a good point. First of all, the F-type only exists in the Tholen classification because the Binzel and Buss and DeMeo classifications don't go that short into the ultraviolet. So essentially, F and Bs are the same unless you're working with Tholen. And so it could be that this object is an F, could be it was a B, and so depending on how you do that. And the Polana family had both the C types and the B types. The B types are dominant in Polana, but it also has some C types. And so it is, and dynamically, the orbital characteristics of 2008 TC3, according to Bill's model, the most likely source in the asteroid belt, it's not only the inner belt, but it would be the Polana family. So, the meteoriticists tell me that Omahatusita is like a 1 in 1,000 case.
Well, yes and no.
Okay. Well, yes and no. And 1 in 1,000 maybe. Anyway, it's supposed to be a rare case, but to me, I think we're still missing something. And what sometimes keeps me up at 4 in the morning is the fact that if one were to, the very first asteroid that we detect outside the atmosphere, goes through the atmosphere, we pick up as a meteorite, the chances are about 80% that it will be an ordinary chondrite. No, it's not an ordinary chondrite. Okay, what is it? It's a Eurolite. Okay, that's about 2% of the meteorites. All right. Oh, no, wait, but there's also 2 types of ordinary chondrites in there. Well, that's even rarer. And then there's enstatite chondrite, yeah, and then there's carbonaceous chondrite. Now, we're talking about a really strange case, and it so happens that that's the first one we have seen outside the atmosphere, and we recovered. The statistics keep me up at night sometimes.
I just want to make one point on that. When meteorites say it's 1 in 1,000, the assumption previously in all the meteorite collections was if you had an individual meteorites that were labeled Uralites, and you found an ordinary chondrite or an enstatite chondrite that was also labeled as part of that fall, you assume that it was been mislabeled by the previous generations. And
hate it when that happens.
And I think we need to reevaluate, and usually you just quietly change the label. And you just tossed another rock into the unidentified pile in your collection. And there's no way of telling how often that happened. So I would very doubt if it was 1 in 1,000.
I am actually secretly hoping that we'll find an Omahatusita type surface on Ryugu and Bennu, although I think Dante will
kill you.
Yeah, well, he won't kill me, but he won't be happy.
Yeah, and I would just say dynamically, we know a little bit about 2008 TC3, but we're pretty far from being able to identify where it came from in the asteroid belt and the rest. It's we need more evidence. We need more clues. I'm puzzled. Okay. So.
You talked, a lot about the Trojans. I'm more interested actually in Phobos and Deimos in their origin, and as I understand it, it's not my area of expertise. There's 2 thoughts. One is that they're both actually remnants of an ejecta event versus the other notion that they are really captured asteroids. Now, my question to you is there any evidence to bias one opinion versus the other?
Well, I could answer that, but our co-chair would be a much better person to answer that question. So, because this is what he does. So go ahead.
I think one of the best appeal to the accretion from ejecta is to explain the orbits of Phobos and Deimos, because you would naturally place them in low inclination orbits. I think compositional-wise, I think Robin's going to talk about it tomorrow at, I'm going to be a little more precise than just some session, like you said. It is, because we have an updated program now. At 1:15 tomorrow in the other room over there, there will be some more discussion about these aspects regarding composition and retention of volatile and things like this. So.
It's really hard to capture things and get them to the orbits where Phobos and Deimos are today. It's not obvious how we haven't come up with a good scheme to do it yet.
Dan, you want to chime in? Please.
I'm reticent to do this, but for the longest time, geologists had a real hard time migrating continents. And they still do, except they realize that continents have migrated. And so the theorists have not caught up with the observation. And I'm afraid that yes, it's hard to conceive of how this could be captured, but it might have been.
I don't think it's a question of being hard, it's the unlikeliness that if you're going to capture not one but two on low inclination orbits, you should capture many more on high inclination orbits.
Well, I think one of the ways you can do that, I understand, is that if you broke it apart in the Hill sphere, essentially reaccreting from a disruption event, that would tend to get into a low accretion orbit. So that's one way.
It has its own set of issues.
It has its own set of issues. I'm not a dynamicist.
I would say that
I don't even play them on TV.
the spectroscopists have a hard time with the impact on whatever the ejection event, and the dynamicists have a hard time with the capture event. So it's a stalemate.
Yeah, deadlock? No, I would say that's a good point, right? I mean,
it's interesting. It's not a deadlock.
So tomorrow Robin will talk about this, and I think it's a really interesting question as to whether you can make Phobos and Deimos spy an impact. I like that scenario because Robin's my boss, but also no. I like that scenario because I think it solves a lot of problems that I've had on this making Phobos and Deimos for a long time. But I think if the spectroscopists ultimately say these objects are really primitive, and like maybe they never reach certain temperatures, that is hard for us to deal with, and then we'll have to reconsider. And I think I think the jury is still out as to whether Phobos and Deimos were always cold objects or whether they could have gotten hot. If you guys can say they simply could not have reached high temperatures, then I think the impact models have issues.
How warm are certain temperatures?
How warm is warm? It's definitely, there's much less impact energy than like a moon forming impact, for instance. But you could still have, few hundred, maybe a few thousand kelvins of temperature.
Few hundred Kelvin would be just fine with me. A few thousand would be a little toasty for what we see spectroscopy.
But we'll hear more about that tomorrow, okay. And there will be discussion, and we're at the end of our discussion slot for the moment. So thanks again to all speakers. We're going to move back after a short break at 3:40 into the room across the hall for a panel on water on the moon.
Amanda, I really liked your presentation, so you